Welcome everybody to this third session of panel 4, Technology, Processes and Systems. My name is Realini. I work for an Italian government research company, and I'm coordinating this panel together with Professor Simon Harvey from Chalmers University of Technology. Today, our session will be focused on new technologies and processes. So we will have papers related to technologies that might be breakthrough to increase energy efficiency in European and over the world industry. We were supposed to have 4 presentations today, but one of the presenters was unable to attend. So we have only 3 presentations, and you can download the 4th from the Whova app and website. We will start with Raoul Laribi from University of Stuttgart that will explain us how to optimize the control system of flywheel energy storage systems. He will compare robust control with adaptive control of these flywheel energy storage systems and explain how to optimize the control strategies. Raoul, the floor is yours.
Thank you, Anna. As mentioned before, I'm working at the University of Stuttgart, namely for the Institute for Energy Efficiency and Production, and pursuing a PhD over there. The title of my paper is Requirements Engineering and Morphological Analysis of Adaptive Control Strategies for Flywheel Energy Storage Systems in Industrial Applications. The introduction is followed in my outline by the definition of adaptive control. Then I will talk about efficiency evaluations and measurements. Afterwards, I'm going to present you the requirements engineering, key requirements. Then I'm going to present the morphological analysis of adaptive control strategies, and finally conclude. The introduction is the following. The German industry is responsible for about 44% of the electricity consumption. Industrial grids, on the other side, have certain characteristics. For example, a high load density, short distances between individual stations, and mainly inductive motor loads. The dynamic and short-term loads often are responsible for a big sizing of the in-feed devices, and although they have a small average load. In these systems, normally, there's a lot of braking energy. So, for example, if a tooling machine is moving its tools around an axis, there's a lot of braking happening and also accelerations. One possibility to improve the energy efficiency on this side is to use a flywheel energy storage system in a DC link. If there's no energy storage system included, you can assume that all the energy is either fed back into the into the AC grid by the active front-end inverter, or converted into heat by a braking resistor, which is marked down here. So one advantage of FES is that it actually can achieve millions of cycles compared to batteries, for example, and doesn't use a lot of rare materials, for example, lithium. On the other hand, there are possible safety requirements for a flywheel energy storage system because there's a huge rotational speed going on, even faster than a bullet of a rifle. So this needs to be designed safely, for sure. On the other hand, there's a lot of requirements for peripheral devices like a vacuum pump because of the high rotational speeds and voltages, and also cooling system. Right. Next slide is taking a while. Okay. So the second chapter of my presentation is the adaptive control. I think there's a slight delay. sorry for the problems. What is meant by adaptive control is that we are adapting the set points for several values. So, for example, the state of charge, the rotational speed of the FES is 1 point. The other one is the maximum current, which is allowed by the inverter, which connects the motor to the DC link in this example. There are two main approaches for adaptive control. On the left side, in this picture, you can see the so-called model identification adaptive control, also short MIAC. It uses a system identification, so it only takes measurements in order to define a model of the system and then adjusts the controller to control the process. On the other hand, you can use theoretical advances in differential equations, for example, and build a reference model, just theoretically. Then the controller is adapted according to the reference model. So it's kind of a white box model of the system. So now I'm going to talk about efficiency evaluations, which we have received doing measurements at certain machines. It could take a while because of data. Right. So, as I said before, there is a system consisting of an active front-end inverter supplying the grid and an energy storage system. If you hear the noises, this is my dog. Sorry. On the left side, there is a power profile, which we have measured for a tooling machine. So as you can see, there's a lot of movement in the axis of the machine. We have a pretty low average load and dynamic load peaks, accelerating and also braking. So accelerations in this example in the positive half plane, and the negative ones are braking processes. We measured also the power efficiency. Sorry, I didn't want to change. Right, on the right side, we have measured the power efficiency of the machine. So the energy which is converted by the active front end. As we can see, there's a cloud around negative or around low efficiencies for most of the time, as you can see about the density. And the high peaks, which is like the actual size of the device, is not so often met in this example. So although we have the load peaks pretty rarely coming up, there's a lot of times where the efficiency is pretty weak. So one possibility is to actually size the active front end according to the loads, which is around the average one, and then cover the rest by the flywheel energy storage system. Right. So we had 3 workshops, including 3 developers and 3 users in our research project, and had discussions about the benefits, drawbacks, and plug-and-play requirements, which led to actually 74 in a number. As you can see, we build up 8 dimensions of so-called fulfillment and tried to cluster them into these categories. The category economic business case, code G, has received the most of the votes, so there's a lot of focus on these subjects in the research project. As I don't want to present all the 74 requirements, I'm just going to have some key findings on the next slide. As we found, the users are interested in a short installation time, for example. If you have a lot of machines where you want to include this flywheel energy storage system and guarantee a high transferability of the FES algorithm, there's a major challenge to actually facilitate this procedure. For us, the use of braking energy is one key aspect, as some machines are not able to be retrofitted. And so the active front end is sized according to its first one. So there's no retrofit benefit from that. Standby losses are a crucial aspect. For example, if you have a lift application nobody uses to lift, it just, the flywheel energy storage just turns around and loses its friction energy constantly. The voltage band used by the energy storage active front end and consumer drives needs to be adjustable, because we are trying to actually use the voltage band and well, take all the energy which is just over the rated voltage, which is braking energy, and over beneath it is actually acceleration energy, which needs to be covered by the system altogether. One classical requirement is the electromagnetic compatibility, which has to be proven, of course. And last but not least, the machine status has to be known at any time for the users. So in the end of the paper, we carried out a morphological analysis of the adaptive control strategies. And if you don't know how this works, we actually try to find solution paths for a certain problem statement. So first of all, we began on the left side of the picture, the table, where we just defined functions which we have to meet with our control systems. Then we tried to have a brainstorming session with certain experts, and of course we are relying on certain experience, knowledge, and also literature research to find the solutions which are suitable for the problem statement. As you can see, the functions which we defined are, for example, state detection, load prediction, control architecture, teaching, and energy management. I can now describe one possible solution path which we think is quite useful. So state detection would be covered by a DC link voltage measurement, which also defines how much energy is in the system at one moment. Then the recuperation could be measured if the main load drive, for example, breaks, and this signal is also fed back to the control system. Load prediction could be done by measurements offline, teaching machine learning approaches. We could use droop control, which means we're measuring the system voltage and then decide how much current the inverter of the flywheel energy storage is letting into the grid or taking from the grid. And this path could be where just follow, and then finally we can conclude that just a second, sorry. Well, finally, we can conclude that there are actually two promising solution paths. The first one is measuring the DC voltage and using droop control, like the characteristic curve which defines how much energy is taken or given to the grid. We also could, of course, directly measure the total consumer current and then decide how much energy is put into the grid by the FES. Also, both of these paths could be combined, because as we are trying to reduce the number of measurement signals, two is also, I think, a good approach. For us, the MEAC approach, meaning the identification with only measurements and not a lot of theoretical approaches, is suitable for this problem statement, as it is transferable to other systems and also other machines. So we're trying to make it as simple as possible and as transferable as possible in this example. So the next steps, which we already began, is modeling the system, of course, taking the data and also trying several machine learning approaches in order to train a model for the system and then control the system accordingly. Well, thank you for your attention. I hope this was all clear for you, and have a nice day. I'm ready for your questions right now.
Thank you very much, Raoul. I remind all attendees that you can write your questions either here in the Q&A or on Huba app. All the questions will be answered at the end of the 3 presentations we will have today. Now, we will have our second presenter, Jacek Leszczynski. I'm sorry if I pronounced you in a bad way.
Excellent, excellent.
From the University of Science and Technology in Krakow, that will introduce us to the double transmission, double expansions technology in order to reduce energy losses associated to the oversize of industrial compressed air systems, especially in the pneumatic machines. So Jacek, the floor is yours. You can start your presentation.
Thanks a lot. I would like to very thank the organizers to invite us. A special thanks to Professor Harvey and of course Dr. Anna. So I am instead of my PhD who get married at the moment, so I must tell us about you know, some topic in pneumatic systems which we practice for a couple of years. So we try to find some industrial ways, not only in laboratory but industrial scale, how to reduce losses or how to increase the energy efficiency. So if you look, if you look on classical energy efficiency of compressed air systems, so we can divide some energy losses into some parts. So we focus here in our solution in utilization state. So we neglect at the moment some analysis. So if possible, I can explain, of course. So we just observing pneumatic cylinder, I mean its dynamics, we find a way that is possible to put the back pressure in small amount in order, you know, to little bit change characteristics, do not perturb normal work of this cylinder. And also if we put some back pressure, so we have some chance to store some energy and after utilize it in the second way. This looks, in my opinion, in close to the same way like in steam turbines and gas turbines, when we have different kind of additional streams which we use it, for instance. So we focus here on this transition state. What is interesting, so classical pneumatic cylinders are oversized by nature. What does it mean? It means that, you know, if you look on the difference of pressure, I mean this pressure is measured in two chambers, two separate chambers. So we observe the dynamics over time. This pressure is like this. So if we release the chamber which was filled in previously, so we release the pressure in this chamber till to the atmospheric pressure. So the next, if we fill the pressure, the other chamber, so another chamber, so we observe that the dynamics is like this, that at the beginning, you see the point, this is the maximal feeding pressure here. And after we observe the moving of piston. So piston is slowly moving and the pressure inside this chamber a little bit decreases. So working pressure here, when the piston moves to change position, is like this. So the difference means that we have the force, the driving force, which is able to change some places, to change some things. For instance, this is normal duty of the cylinder. So our idea is like this, that if we keep this distance, this difference, this pressure gauge, so and only change, its characteristic for this, we have a chance to store some pressure which will be from this channel. So we have, we have some different methods which we try to improve efficiency of the cylinder, of pneumatic cylinder. So if we focus on this, so this is our method which we introduced to the existing literature. So we, as I told before, introduce small amount of back pressure, and this is able for us to store this energy and after utilizes in the second stage. So we call this double transmission and double expansion. And we explain it maybe a bit more in this PV diagrams. So this is responsible for different kind of process realization. If we focus on our solution, we have this that if we introduce this back pressure here, so we divide this field into two fields. Of course, we decrease a little bit, I try to repeat a little bit, the power of the machine. However, we have this field when we store the energy, store the work. And also, another good is that we reduce the dead volume work in all pneumatic systems. So this is another interesting thing. So of course we can calculate air energy savings, which is work of some method till to the work of conventional classical circuit. We assume here in this solution, in order to simplify the calculation, that every process is isothermal. And also in the second stage, we produce the electricity, for instance, and put it into the network. So we assume some coefficients, which we explain in more detail in our full paper. So what I would like to show, so we validate our model with real work of one pneumatic cylinder. So in order to observe the dynamics, and of course, if we introduce the back pressure to one cylinder, we observe what will happen. Especially here, we introduce, at the beginning of the theoretical consideration, we still keep this distance to change the pressure difference. So a little bit change the characteristics of the moving rod or moving piston. It is a small change which does not have any influence on normal work. We can, of course, explain in more detail. So maybe I do not explain you some details because we see some air consumption and air savings. This is explained in our full paper more detailedly. So Carol, can you run this movie in order to show our machine, our energy harvester unit? I mean, this is the machine which is responsible to utilize the stored energy. So it composes from, let's say, slider crank mechanism, and which is connected due to some gears with power generator. Our generator is somewhere downstairs here. Here, this is the power generator, 1 kilowatt of electric power. It is normally registers some parameters, some technical parameters, but just you see here on the left side the tank which we store the energy. And of course, maybe the interesting thing is that this machine works on very low gauge pressure. I mean that it works in the gauge pressure of 1 bar, 1.2, 1.3 bar, 0.7 bar. So this is, you know, its advantage, for instance. So to construct the machine, you see, it is very heavy task, and it is, this machine is connected also with the network. We will see maybe if possible to go. I don't know how to speed up this maybe, because it is a couple of minutes. You see, this is the pressure tank, which we note gauge pressure of 1.25, but we remember. This is, so this machine works in very low pressure gauge. So this is the advantage. You know, this is the second stage for, so the machine is feeding from the first stage, from the original or regular pneumatic installation. When we introduce some back pressure in some ports when mufflers were located. So we move out the mufflers, build some collectoring system, and after we utilize, we store this, it is in the bottom part, we store this energy of, let's say, waste of air in this tank here, in this tank, and after we utilize it dynamically in our system. So this is very good because this system can trigger to the actual situation, whether mean the change of volumetric flows, for instance. So we can trigger it. So sometimes we observe in electrical power, because this is the last observable, that we observe, we see 1 kilowatt of electric power, or maybe less. Oh, you see, this is the effect. This is the exit effect. So if we utilize the waste of energy, we can fit, you know, some lights or this is the inverter, which is responsible to put the energy to the regular to the AC network. Yes. So this is our machine, our small achievement. We practice it for a couple of years. We start to build this harvester in small scale when the generator power is 20 watts. So now this, you see, this is the unit which is able to put the energy, the power, the electric power in the amount of 1 kilowatt. So please, Carol, stop it and back to the slides if possible. Thank you very much. And the next go to conclusions. So we observe that it's possible to put the back pressure to all pneumatic installation. Of course, it should be done in, let's say, intelligent way in order to do not disturb the normal production. So we made 6 industrial tests, which operating, I mean, the feeding pressure was, gauge pressure was 6 bar. So we find that we can put the back pressure 1.5 bar, which is okay for normal or regular work of this pneumatic installation. And this storage energy or waste of energy we can utilize using our energy harvesting system, which we'll see which we seen on this movie. So thank you very much for your attention. I don't know if I crossed the time, so please. Thank you very much.
Thank you very much, Jacek. And if anybody has any question, you are welcome to write them here in the Q&A section. You can find on the bottom of your screen or in the Huva app. The panelists will answer them at the end of the presentations. Now we go to our third presentation that is focusing on energy efficiency seen from another point of view. Or let's say we are used to think about energy efficiency as something that has is in the machines, so we have to optimize machines and so on. Andreas Pastowski from Wuppertal Institute of Climate, Environment and Energy will present us a new perspective on how to achieve efficiency while using additive manufacturing with metals, or how to reduce material consumption and increase energy efficiency. And he will focus on wire arc additive manufacturing and present us some results from the reInvent project. Andreas, the floor is yours.
Yes, thank you very much, Anna. Hello to everybody. There is some incoming sunlight now, which may create some very bright spots on me. But, well, we have to take it as it is. And well, if we take a look back into the past, it was about 20 years ago when there was first mention of 3D printing as a potential new processing technology that may allow to increase the energy efficiency as well as material efficiency. Well, first of all, there is a lot of mention of 3D printing and additive manufacturing. Basically, we are talking about the same things. Of course, the printing analogy is a little bit strange in terms of using metals, because most of the AM processes with metals work at melting temperatures of the respective metals. So you can see by that the analogy is not that straightforward necessarily. But taking a look back into history, even at that time, 20 years ago, people had very high expectations as regards the efficiency potentials of additive manufacturing. Then came a time, I would say roughly 10 years ago, it started when people could produce their own homegrown 3D printed plastic toys, or some have even produced weapons, which is not so good, using a printer that uses plastic material to build up 3D objects. And now, 10 years later, we are at a different stage, because now we are really at the point when 3D printing, or AM, is entering into the manufacturing domain. But still, we have to be aware that 3D printing takes some time, and therefore it may not be the best processing technology when it comes to producing mass-produced items, because in that case you will necessarily need to be very fast in producing these items. Otherwise, the capital investment will be simply too high, and other things may negatively affect that kind of production technology. And therefore, it still needs to be found out which exact products and materials will deliver the highest potentials in introducing additive manufacturing. Well, that is just to let you know what we are talking about. Then, I don't have control of the slides, sorry. No, still not available to steer to the next slide. Yes, very good. Yes, what is the significance of AM with metals? We are at a stage that allows to draw at least some preliminary conclusions as to how additive manufacturing might impact on energy efficiency. In the past, there was a lot of enthusiasm, but hardly any proof for that. But today we are in a different state where additive manufacturing, in particular, in some areas, for instance, medical implants, and even more important for aerospace components, have become a reality. And the aerospace components are specifically important to be constructed in a way that they are as lightweight as possible. And therefore, we saw a lot of application in this area with somewhat bigger, more voluminous parts, which are designed for additive manufacturing. And often it is also the metals aluminum or titanium are used to do this. Steel applications are not at all common in aerospace, of course. But of course, we can also imagine, I will come to that later on, also applications where steel may also play a role in additive manufacturing. Yes, and what comes to mind here is also that with many cross-cutting energy efficiency technologies, there's hardly any impact on other stages of the value chain and how energy efficient these other stages of the value chain perform. But with additive manufacturing, there can be very important impacts on that, even until final use. And the lightweight aerospace applications are a good indication of that. And therefore, there may be much more important repercussions on other stages of the value chain than what we have seen before. Yes, next slide, please. Yes, and here you can see that there are numerous additive manufacturing technologies that can be used in general, and you can see here in green the different starting materials, but also kinds of material preparation that are available with additive manufacturing and where metals can play a role. Next slide, please. Yes, and the reInvent project has been mentioned, and one of the reasons for me to go back to additive manufacturing or 3D printing was simply the reInvent project, because we had one case study that took a look at wire arc additive manufacturing. And wire arc additive manufacturing is basically using welding robots to build up 3D objects. So what you can see here in the picture is the main part of a pedestrian bridge that was constructed for use in the city of Amsterdam. And you can see that the shape is very unique. This is something that might probably be achieved by casting, but there is no other processing technology that allows to achieve such unique forms. And what you also can see is that you can see here is the welding layers, because the welding robots are putting drops of steel to one another. And we are here talking about steel, of course, because it's a ground application and we don't need the highest lightweight potential to be achieved. And which means that the surface quality may look in a way that may add to the overall look of what we are looking at here, because this is, well, you may have seen similar structures in movies. In science fiction movies, some spaceships may have looked like that. And well, this is something that is very unique, and what is also very unique with 3D printing, to mention that at this point, is that you can even construct bubbles into 3D objects, which there is no other processing technology with metals that allows to do this. So yeah, this is very unique. And the look is also unique, but it might also, for certain applications, in particular for wire arc additive manufacturing, need some post-processing to achieve a certain level of surface quality that may differ from what you can see here. Next slide, please. Yes, and the drivers of value chain-wide energy efficiency, they are distributed, or they may be distributed in a much more diverse manner along the whole value chain. This is what I have already mentioned. And what are the main drivers of that? Well, of course, we are first looking at AM energy intensity as a processing technology as compared to other processing technologies. So this is the core area of the processing technology where we may see different energy use as compared to conventional processing technologies. But what is very important is that with AM, you basically only use a volume of material that will really end up in the final product, except for some processing, surface processing, probably, but that will only cut off very limited volumes of the material used. So this is a strong factor in using scrap, in reducing scrap, and only using the material that makes it to the final stage of the supply chain. Well, another factor that is more or less combined with the material efficiency is that you have to transport less material simply along the value chain if you are only using the material that makes it to the final product. And what comes on top is, and well, airspace, the aerospace industry is very indicative of that. Longevity may play a role because of on-site repair that may be possible using AM with metals. So you don't have to warehouse as many parts, important parts for steel work, for instance, in which case a failure may cause the whole plant to be stopped, locked down effectively, and therefore they are keeping a lot of repair parts and in a warehouse to not let that happen. And on the other hand, there may be also, and this goes particular for transport applications, and in particular for transport application above the ground, where the carbon intensity during the use phase may also play an important role, and where AM may allow to reduce the weight of the vehicles that are used, and by that also reduce the energy consumed. Next slide, please. Yes, so we can sum up energy efficiency as compared to the respective conventional processing technology is a core area. Then scrap intensity and material efficiency are important. Transport intensity, that is more or less combined with that, is important. But there may also be some shrinkage of the supply chain. There may be less number of places where the supply chain resides, and therefore also less need to transport in between those stages. And as mentioned, longevity and end-use carbon intensity of the utilization of final products. Next slide, please. Yeah, so we can come up with a preliminary assessment of AM with metals with regard to energy efficiency. And you can see here that there are, on the top, are the various use cases of metal objects that are processed using additive manufacturing. And of course, aerospace components, that is the driving technology part at this point in time, because that allows to achieve very high paybacks resulting during the use phase. And therefore, there's a lot of research and development in that area. And the main metals used there are titanium and aluminum. The material efficiency is always increased regardless what application you look at. Of course, the metals that you use will differ depending on the application. As you can see here, aerospace and ground vehicle components, you may see more aluminum, while in the other use cases, steel may stay to be the predominant material used. Yes, and supply chain transport efficiency is generally important to some extent, but it will be more important even if you come to on-site production, where you shrink the supply chain very much, and therefore also shrink the volume of transport that is necessary, and on-site repair, because you may reuse some functional parts that are worn simply by using some technology like wire arc additive manufacturing to add the necessary material, do some post-processing over that, and use basically the same part again in your production process. Well, an end-use energy efficiency clearly has the focus in terms of aerospace components and ground vehicle components. Next slide, please. Yeah, so to come to the conclusions, it can be expected that the contribution of AM to decarbonization of metal value chains can be very substantial in cases where it may allow to combine the following. First of all, higher material efficiency during the processing stage over conventional, in particular subtractive manufacturing processes. Then the geographical compression of value chains by reshoring certain steps of them. And finally, increase energy efficiency during the end-use phase of the respective products by reducing their weight. Well, of course, any robust assessment will require further research with a focus on energy use and decarbonization potential of AM with metals. And of course, there is quite a bit of topics that could still be worked on. Well, so this is my presentation, and I would like to thank you.
Thank you very much, Andreas. Now all the panelists are invited to switch on their camera and microphone to participate to the Q&A part of the session. Jacek, can you please switch on your camera as well? Okay, so since I think our attendees are quite shy, I would like to break the ice with some questions myself. First of all, for Raoul, your presentation is very interesting, but I think that what you were presenting is not so common in industry now. So can you please introduce us to some practical application of flywheel energy storage systems and whether you have planned any industrial trial or case study? Okay,
yeah, there are actually a lot of applications for energy storage systems like flywheels. For example, an electric car is just fed by electric storage mostly. So there's a DC link buffering all the braking energy, which is then through the driving sessions. And also, of course, lift applications, elevators, cranes, for example. Also, charging stations for electric energy. Electric cars are sometimes newly fed by flywheel energy storage systems. For example, at the airport of Vienna, I guess there's a project at the moment.
And are you planning to try your
yes.
your model on any industrial case study?
If someone knows the company ThyssenKrupp, for example, they have a huge tower where they are testing their elevators. So it's a site in southern Germany. And they're one of the applicants, and the other ones are manufacturers of milling machines. So the usual ones which have a lot of axis movements, a lot of braking and acceleration.
Thank you very much. Okay, so, well, Jacek, are you there? Meanwhile, I invite all attendees to write their questions if they have any. Okay, I can't have a feedback from Jacek. So, Andreas, to you. So you mentioned several times that one of the constraints of additive manufacturing is time. I understand that your analysis is just a preliminary analysis and some research work has yet to be done. But have you considered or have you already started any life cycle assessment of the impacts of additive manufacturing with metals compared to traditional techniques? And have you taken time into account in this assessment?
No, so far we have not done this. Of course, with the bridge, and we have, when we talk about time, we have to keep in mind that different time spans are important in the whole process. But when I was referring to time, I was simply referring to the processing with additive manufacturing, and compared to almost any other processing technology of metals, this takes more time than what you usually would need to do this, even though you can also do things that no other technology can do at all. And therefore, in that particular case, time may not at all be a constraint. And if you not only restrict the consideration of time to the stage of the processing, but if you look at time to market, then that may be an entirely different story, because you can very fast design new products which are very specific and with very specific features also as compared to what conventional technology can do. And when you then take a look at time to market, then that may be very rapid. But at the same time, you need to keep in mind that if you want to mass produce anything, stamping may be much better, much easier to do, for instance, even though you lose some of the material in the stamping process. But if we are talking about the bridge that I have shown, well, as far as I can recall, that took several months by wire arc additive manufacturing to do this. Even though, considering the whole process, it must not necessarily have been that long. It may even have been shorter. And many technologies, processing technologies, would not at all allow to achieve such a design. Casting, maybe casting of several parts and welding them together. That may be a way to achieve a similar design that we have seen with the bridge.
Yeah, that's more work of art, let's say, from the pictures you presented in the slides. And I might have missed it in your presentation, but what about economics? You reduce the material loss and the material waste, but how much does it cost to have such technologies compared to a traditional technology?
Well, if we are talking about wire arc additive manufacturing, this is basically new software, because the welding robots already exist for quite some time. So this was no new invention. The only thing was to do the CAD translating the CAD results into the welding robot movements. So that was the main work of MX3D, who have done that. The welding robots already exist, the steel wire exists, so that is not really new. But there are also other cases with powder bed fusion, for instance, where you are using electron beams or laser beams to melt the material and form the 3D objects that you want to achieve, where you are maybe more limited, because that process takes time. You are always stepwise lifting the object up again. You need to create a new layer of powder above it to create the next layer. So that is really time consuming. And I cannot imagine that to be as fast as many subtractive technologies that we have today. And also casting may be faster. So the speed of the process is not exactly what we can expect to achieve the biggest improvement of that technology.
Thank you very much. Is there any other question? I see Jacek hasn't come back yet. So all the attendees are warmly invited to ask questions, or if any of the panelists has a question for the others, it's good. No? Okay, so
I have one question for Jacek, but...
okay, Jacek is back. Perfect. Go on, Andreas.
Well, I have had at least some look at compressed air systems, and the main energy efficiency issue with those systems is that you almost always have leakages in the system, and that nobody cares sufficiently well about getting rid of such leakages, and that one reason for over-design, for oversizing this whole system, may be that you will always have some leakages somewhere, and if you design it specifically for the volume without leakages, it will not work. And yeah, I don't know whether that is true, or whether somebody has told me a fairy tale with regard to this. So I would like your view on that.
Well, so if I correctly mean, so we have a lot of losses, I think, in pneumatic installations. One of them includes, of course, leakages, which we do not analyze here. So we only focus on, you know, some waste of energy, which is which grows on expansion process. Expansion process means that if you fill the pneumatic cylinder, you must release it, some chamber, you know, in order to make the movement of the piston. So, and what this expansion is realized in real pneumatic system. We use mufflers, you know what I mean, mufflers, in order to reduce noise. And the expansion dynamics is like this, that we expand starting from the feeding Gauss pressure, means 6 bar, till to the atmospheric pressure. However, if you analyze the muffler dynamics, so this is more complex, because the muffler initiates some back pressure. And what is the amount of back pressure which is initiated by the muffler? It depends. If we have clean muffler, so we observe that the back pressure at the beginning of the expansion dynamics is almost 2 bars, for instance, 2 bars of Gauss pressure. However, if we have the dirty mufflers, for instance, so we observe that the back pressure given by mufflers are in the amount of 3.5 Gauss pressure, when we, of course, start with 6 bar of pressure. So we have, you know, we observe in natural expansion, in natural work of pneumatic installation, that every installation is oversized. So I'll also bring your attention of my last 2 papers published in Applied Energy. So I can send you after, if possible. So you will see some details how we can do it. And we focus, you know, only on expansion energy here.
So one further comment. So you are basically dealing with some compressed air waste that has already been used in one process, but that cannot deliver any physical work in that process anymore because the pressure is too low?
Well, you are talking about the back pressure, yes? This back pressure when we introduce the low, yes? Of course, the tricky, or maybe in scientific way, what I like to say, is the level of back pressure which is able to do not put any disturbances of real working, industrial system. So, and by the way, we have also good contact with professor from Stuttgart. I forgot the name, Professor. I forgot the name. I will repeat, of course. Who is also very familiar with pneumatic systems, and we discussed some idea of this was accepted. So now, we try to increase energy efficiency of the compressor. For instance, if you imagine some scenario that we have one compressor which is able to feed one pneumatic machine in the same manner, I mean the energy or electrical energy which is necessary to feed, to change, to compress the air and to feed this machine. And this machine is operates in normal way, and after, due to expansion, the compressor is decompressed to the atmospheric pressure. So if we introduce the back pressure in this machine in some amount, I mean that if we have the feeding pressure 6 bar, if we put the back pressure 1.5 bar, so we can reduce the electricity of this compressor of 14%. And also, maybe the second question, or maybe some doubt of this, that why we do not reduce the feeding pressure? Yes, because this is natural. So no, it is impossible, because if you have the machine which is works in normal 6 bar of feeding pressure, you cannot reduce the feeding pressure because you perturb the normal or regular work of this machine. You cannot do it. So
Okay.
maybe too much to express. So just I can send you. Maybe in my biography there are some links for papers published in the last 2 years. So there are a lot of details about it.
Yes, I will take a look at that. Thank you.
Or if also, please write me. I will send you these papers. Okay.
Okay. Is there any other question? If not, I thank all the panelists for their interesting presentations and all the attendees for staying with us during this session. And I invite you to join other sessions of the conference today. And we will have 2 new sessions of Panel 4 tomorrow at 12 and at 2 Central European Time. Thank you very much and have a nice day, everybody. Bye-bye.
Thank you, Anna, and everybody.